All right, on to the last of the QHack challenges, QHack 4, which is variational quantum eigensolvers in Pennylane. So this is something we've talked about a lot before, a lot. So, and we'll talk about more too. There's a technique I'll bring up here that I'll also talk about later explicitly in its own format. But let's just get right into it. We can see problem 1 right off the bat is always the simple one. In this case, it just introduces VQE, and we're given the input, we're given the starting set of parameters, and we just have to minimize it using Pennylane. So we can see that, once again, I'm going to uncomment the print statements, but recomment them in the upload. We can see that we're given the variational ansatz, we're given the Hamiltonian, and what we can do is we can just minimize it. So we use the Adagrad optimizer. This is actually, I use the exact same optimizer and learning rate for all of these VQEs. For whatever reason, Adagrad optimizer 0.2 learning rate seems to work the best. I'm not entirely sure why, to be honest. Then we do 500 iterations, and each time has to decrease at least 1 times 10 to the negative 6th energy. And so we can see that we this time we use step and cost, just returns in new parameters into cost function evaluation. Previous with the old parameters, and we can see that this we're measuring the change from old cost to new cost, and if this is less than the tolerance, then we break. And so we can plot this over time, which is exactly what I will do. So we can see that this will take just a little bit to run. Hopefully it'll open up. Yeah, so we can see it's steadily decreasing. It doesn't go for the full 500 iterations. It just goes for 160 iterations. And so we can, if we type, we can see that's the correct answer to a suitable fluctuation. It's like plus or minus 0.01 or something is what you're allowed. And note that I'm not really discussing how to do this Hamiltonian or what quantum chemistry applications Pennylane have. This is just for this problem, which you can read because they're all online. How do we solve it? And so in this case, it's really straightforward. All we have to do is just use the standard optimization, just using this xval cost, or saying the cost function just is the expectation value. In this case, is all that's defining, rather than saying cost function is just, we could define cost and then run the circuit and return circuit of params. But this time we're just saying the expectation value is the cost. And notice this handles everything for us here. I want to emphasize that. In Circ or TensorFlow, you might add, we might think, okay, we have to input the Hamiltonian or something. Notice H Hamiltonian handles all of the addition. It gives us one value. So we get one number out of it, which is the approximation of the lowest eigenvalue. And so this is nice because we don't have to worry about anything. So it sort of abstracts it away into this Hamiltonian. So getting into the next one, this is probably the one where I did the worst on. This took me the longest actually, because in this one, we're supposed to generate the quantum state. Here you can see the quantum state has only one value. So it's a superposition of 1000, 0100, etc., all the way to 0001. And so this is kind of hard to generate, but I'll mention two things. One, there's actually a state called the W state. So I'll go over. So the W state, let me go back, generate that. So two things. So we have the W state, and this is a famous quantum state. It's a form of entangled. So we know the Bell state. is there's different forms, but this is the usual form you'll see it in. So we know that's the Bell state. The W state is another form of strong entanglement, typically represented. Once again, this can be, just like the Bell state can be extended, so too can the W state. Actually, the Bell state, I think, is specifically, I think it's a GHZ state or something of extended, but the W state can't be extended. We'll see this as, this is what it is, 0, 1. And so you might notice, hey, wait a minute, this state right here is the exact state that we need, just with changing the amplitudes of the wave functions for each of these values. And so I looked a lot into creating that, and I do create the W state for the 2-dimensional, or for the 2-qubit wave function. It's also worth noting there's a paper that's good here. It's called the Improving Hamiltonian Encodings with the Gray Code. I only found this after the hackathon. Interestingly, this was dated February 9th, 2021, so this came out literally right before it. But in this paper, they present the Gray Code, which is kind of similar to using the Gray Code for Hamiltonians, which is pretty much very similar to our goal here. However, I only found about this paper after, but I'll still, show it. So in the first case, we have, so I have two situations here. We can see this is the circuit that we're creating. And in this case, we can see if it's the 2-qubit system, then we create the W state here, which is this rotation up front, followed by a C0 and a X gate, which should be, I believe, the W state. And so then we can just change the rotation up front. And then the second one, I do not use the 3-qubit W state, nor do I use the Gray Code. I do something that just happens to work, and that is RY gates and C0s. And so this isn't exactly the same as what we're trying to generate, but it ends up working. So I guess that's all that really matters. And so this time we have the weights of the different systems are dependent on the number of qubits, so we have different formats for them. Once again, we set the same random seed because it's always good to have that. We measure the number of qubits, and we set, once again, the expectation value cost, which sort of abstracts away all of the details of the Hamiltonian and the addition of that. We use the Adagrad optimizer, once again, 0.2 learning rate. We have a slightly lower tolerance here. Not really sure why I made the lower tolerance, just happened to work, I guess. But this code right here is exactly the same as over here. I just copied and pasted it because, once again, all we're doing is minimizing. The goal of this challenge was simply to create these variational ansatz that are different. And so for example, the first thing I did try to do is copy this. I believe this is the hardware efficient ansatz over and try and work with it, and it does not work. It won't find the lowest parameters, but these do. So for example, if we go over and we Pennylane, and we go into the QHack, we can see that this will. So this is the 2-qubit system, by the way, that has we can see it reaches it very quickly, as a matter of fact. So if we do type advanced, we can see that's within the error tolerance. And we can do the same thing for the second input. This one I think takes a little longer. But keep in mind, the first one was able to converge so quick, partially because we used a high learning rate optimizer, but also because that is actually the W state that we're creating, or the desired ansatz, whereas this one is I think will take a little bit longer, just because this isn't exactly the desired outcome, because we're doing more of a rough approximation, if you will, of this desired setup. And so we can see this one will take about, I don't know, I think it will take about 140 iterations to converge, but it will converge on the right answer. And this one actually took me the longest, just because I tried forever to create the W state exactly in Pennylane, because I don't know a lot of the Pennylane ops. But we can see here that it reaches a satisfactory optimization format, or satisfying optimization minimum. So now we can go and see. This is the very last of them, and this is something I'll talk about more later. But this is another good one, like the circuit training 500. This one, you just had to find so normally with the VQE you find the lowest eigenvalue, and this one you find the lowest 3 eigenvalues. And so there's a number of modifications that have been made to the original VQE to allow it to find higher order, higher level excited states, is what they're called. And in this one, so there's a couple algorithms. Some of them, I tried one of them. I can't remember what it's called now, but it required access to dev.state, or to device state, which you saw in the Fubini study metric. And I didn't like using that because it's kind of cheap, you know. But in this one, I used a technique from the 2019 paper Subspace Search Variational Quantum Eigensolver for Excited States, from the University of Tokyo. And so this one is very simple. Basically, you create, here, I'll go back to the drawing board. So for this, we have SSVQE. So SSVQE, this is just a brief overview, because I'm going to talk about this more later, specifically with Cirq and TensorFlow Quantum. But normally, right, we have the minimization that we're doing is this sort of format, right? We want to minimize this. In this case, all we're doing here is we're doing the exact same thing. This can also, by the way, be written as, this will be helpful later. So we're starting with the 0 state, and we're, because the 0 state is sort of just implied in this. So the SSVQE sort of changes this and says, okay, we're using the same parameters, the same parameterized wave function, but then we're minimizing the sum, where this is, it should be an I probably, or yeah, make that an I, over however many excited states we want to find. And then we're doing yeah, I guess I can write it as this, or I guess I'll copy their notation. So in this case, it's very similar to, you can see the similarities here. However, the difference is these states, so I'll write this as this. So for these starting states that we're starting the VQE from, they're not equal to each other, and in fact they have to be orthogonal to each other. And so normally, it's a fancy math term, but really all this means is, if we have a multi-qubit system, this state is orthogonal to this state, which is orthogonal to this state, which is orthogonal to this state. And so there's a lot of options here. It's really not that hard to create the orthogonal states. And then for every increasing excited state, this weight value decreases. And so this is sort of a hyperparameter that has to be optimized in some sense. So I sort of guess and check to optimize this hyperparameter. And we can see, this will make sense maybe when we do more of it in code. So we can see that in this case, we have 3 different ansats because I combine them sort of into I combine the parametrized wave function and the starting state just into one circuit. I don't know if this is the most efficient way to do it, but this is how I do it. So we can see that this is the starting one, and this is kind of just a common sort of like the hardware efficient one, just a more compact way of writing it. So it's an arbitrary rotation gate on each of the qubits, followed by C dots connecting every single qubit to each other. And so these 3 circuits are exactly the same, except you notice before each of them, so this is a starting state, right? The starting state for this one is just all zeros, but the starting state for this one is all zeros except for on the first, well, not the first, the wire equals 1 qubit, because they start at 0, so this is really the second qubit. And this is has a Pauli X gate on the first one, and so this is to make them, these initial lines make the initial the input states orthogonal to each other, which is a prerequisite for this to work. And so once we have them, we can create the devices. They're all separate, and we have the cost functions, which are just using these separate devices for each of them. So this is ground state, first excited, second excited. We have a low tolerance here, same Adagrad optimizer as always, and we can see here the cost function is different. It's a linear combination of all of these cost functions. So we can see that for this increasing excited state, the weight decreases. So we can see for ground state it's 1, first excited state is 0.65, and for the second is 0.55. And there might be some intuition here, but I don't really have it. I sort of just guess and check to generate these values. And so what we do is we use the same set of parameters for every single state, for every single function. We just change the initial state. And so we only have to optimize one set of parameters. So we do a step in cost, and we can see that in this case, I'm just choosing to evaluate the tolerance. Actually, I should just do just do cost here. And so here the energy isn't exactly the same, because I'm just clear. The energy here isn't really the true energy. This is the combined cost function, but we have the tolerance set to be the same as before, and we're just printing out. So this is the we're printing out the energy, and then for each of them we print out what iteration we're on and what the cost is, or what the energy is for each of them. So they should converge to each of their values, and then we set them equal at the end. So you can see that the optimization loop here is pretty much the same, except we just have a different cost function, which is defined by these orthogonal inputs. So if we run this code, then we can see that well, the setup, once again, always does this annoying little heading, because I tried to use Pennylane with TF, which is kind of unfortunate. But we can see, so this is the total cost function at the top, and then these are each of the energies. So you'll notice they won't all converge to the same value, because they are converging to the higher state. And this one takes longer because we're doing many more evaluations of the cost function. We're doing 3 times as many cost function evaluations, because the total cost is a linear combination of the of the individual costs. So I'm just gonna pause this real quick. Just you don't have to wait for the whole thing to execute. All right, now we can see that the optimization loop has converged, and it's converged to the appropriate answers, at least close enough. Note that this one has a higher tolerance. I believe it's 0.03. So even though this one looks different, this is about 0.03 away actually, because it is an approximation. But you can see that it converges to pretty similar to the lowest ground states, and it takes 120 iterations. We were also given more time for this one. So now I'll run the second one, and we can see this once again. I'll just pause while the optimization loop completes. So one thing I do want to note here is you can see that at times the energy function may be above or below the actual desired energy for a given state, and that's because we are optimizing for all of them simultaneously, not just the given one. We're not just trying to minimize one of them. So one of them might be lower, but that's because it comes at the cost of the others. So we're balancing these three linear combinations. And so now you can see the second one's running right now. I will pause temporarily for that. Okay, now the optimization loop has finished. You can see the tolerance probably should have been set a little higher because it just went around the same sort of values for a while, but you can see it does converge to the correct values, negative 1.3, negative 0.99, and negative 0.32. And so we can see that how to create the higher order excited states via a modification of VQE. And this is actually something I'll discuss more, and I'll discuss the paper more, so don't worry if it's not entirely clear. And that's all of the QHack challenges. There's only 4 sets of them.